usually try to picture what they look like. We've done that for thousands of years. There was an ancient Greek guy named Democritus. He and Aristotle had a lot of debates about what matter was. Aristotle thought that all elements were either earth, wind, fire, or water, which obviously is not true. But then Democritus just started thinking that everything that we have, all matter, is made up of very tiny particles that can't be split up. Years later, a guy named Thomas Dalton came by and came up with his atomic theory, which had a handful of postulates in it, or rules essentially, for what atoms look like and what they do and how they interact. But then we started getting into the visual models around 1904 with J.J. Thomson. This guy had discovered the electron before he came up with this model, realized that there was a negatively charged particle somewhere in our atoms, but he kind of theorized that kind of looked like plum pudding or what we might think of as a chocolate chip cookie today. Basically, the dough in it is made up of positively charged goopy stuff, and then the chocolate chips, or the plums in his model, are the negatively charged bits spread throughout, just kind of randomly. It looks a lot like this would be a picture of plum pudding. And then, so all of this blue here would be positively charged goop or dough or something like that. And then these negatively charged bits just spread throughout. Rutherford came along and did an experiment that helped to define better what an atom looks like. He actually gave us the idea of the nucleus. He performed this experiment where he shot radiation particles called alpha particles through a bit of gold foil, and he expected one thing. Something slightly different happened, and we'll see that on the next slide. But basically, because of that, he theorized that there was a positively charged mass in the middle of our atoms. So his experiment, he shot this radiation, these alpha particles, straight through this gold foil. Because of J.J. Thomson's model, there's nothing for them really to bounce off. The electrons are so small that compared to the alpha particles, that the alpha particles wouldn't be affected. So when you shoot it through J.J. Thomson's model, it just goes straight through. And that's what most of the particles did. But you'll notice over here, some of them bounce off to the side and go every which way. That led Rutherford to believe that maybe there's a small bit of positively charged stuff that's bigger than an alpha particle that can bounce an alpha particle away, while the rest of it is just empty space with electrons filling around it. And that's basically kind of what we think of today. Rutherford's model was suggested in 1911 after he did his experiment. The one thing that's weird about his is that he didn't really know what to do with the electrons. He just thought, okay, there's a nucleus, and then outside of that nucleus, there's just electrons taking up space, bouncing around, moving randomly. Niels Bohr came along, though, and he started looking at some stuff. He realized, well, in 1913, he started doing some experiments. When you excite gas particles of hydrogen or helium or any other element, you can see that it releases specific beams of light. And if you look at that light through a diffraction grating, you can see the very specific bands of light, kind of like a rainbow, but only parts of the rainbow at a time. There's like fingerprints for the atom. We call it the atomic emission spectra. That led Niels Bohr to the idea that those electrons in an atom only exist at specific energy levels. They don't just exist randomly. They have very specific energies associated with each of them. And those energy levels are represented by orbits or circular paths that the electrons would take around the nucleus. So same idea kind of as Rutherford's model, but instead of just electrons randomly throughout, they're going around in a circular path. These are some of the atomic emission spectra of different elements. You notice there's only these small bands of light that you see here. Again, those are like the fingerprint of that element. That tells us where those electrons exist energy-wise and exactly what element it would be. So the two main differences between Rutherford and Bohr is the placement of the electrons. If you're looking at the movement of electrons, it kind of looks a little randomly here, but you can see they're going around in a circular pattern. It's just at a different angle for us there. But you have all the positive charges and neutral charges, the protons and neutrons, stuck in the middle there, called the nucleus. Now you might wonder why all these positive charges are stuck together in the nucleus. We know that like charges repel each other. Why do positive charges stick together in this case? Well, there's a force greater than the repulsion of charges inside of an atom. It's called a nuclear force, which is kind of similar to gravity. It's because these protons and neutrons are so big, they pull together to each other and stick together, despite the fact that these protons have positive charges that repel each other a little bit.